For this homework, we will use jump. It's also important to know how to solve the problems by hand. So if you're practicing up for the test right now, try doing everything we're going to do in jump for this homework by hand. If you're trying to download jump, look at the other videos on this channel and you'll find the instructions for how to download jump onto your computer. So we're going to take the data from the table, going down here to make tab delimited copy. We click it, and we now have the ability to paste this data into jump. Right here, we have a jump table. I've started up jump and it is completely blank. I have not clicked anywhere in here because that can often cause errors. I am now going to paste with column names. You can go under Edit, Paste with Column Names, and do it like that, or use Control-Shift-V if you're on a PC. So now we have the data in here. It's very important that we see quantitative, very important to doing regression. You'll notice that age is at the top and so is price. These are the column headers and they allow us to analyze it. If you have age and price down here and these are red, that is bad. If you're on a Mac, a lot of times you'll see a spacing. It just happens. Don't worry about it. Jump will skip over those. And it can kind of help later on in this problem when we do some estimations, putting in a value. So let's go ahead and take a look at this problem. Find the equation for the regression line. Now you could work this out by hand and it would take quite a while, or you can go to Analyze, Fit Y by X. We need to use age to predict the price of a car. So when we use age to predict the price of a car, we will get this sort of relationship right here. With that in mind, we can now fit a line. I'm clicking under the red arrow to fit a regression line. This is the line of best fit, the line that goes through the data as best as it possibly can, getting as close to all the points as it can. Now we see the regression equation below here. An important thing to notice is that it is negative. The slope is negative. What we see right here is that when a car is brand new, the intercept, we would expect someone to pay $14,278. Why is this? Well, the intercept is when age is equal to 0. And that'll help us out for some of these problems. The slope, very important to interpret also. The slope for this is for each additional year or age, a car will decrease in value $956.80. We need to make sure we can interpret the slope and the intercept in context of the problem. And for this problem, the intercept and the slope make sense. We know what a car with 0 years of age is. It's basically a brand new car. And we know that as a car gets an additional year of age, it's going to decrease in value, generally speaking. Next, another value for us to look at will be the R squared in this problem. For the R squared, we see right here 0.9456. And this is just correlation squared for this problem. This means 94.56% of the variation in price is explained by age. Very important to interpret the R squared. Finally, is this model or parameter significant? And that can be answered down here. We can look at the parameter age in the model and look at its level of significance. And yes, it is significant. We are looking at age, the parameter in the model, which is our x. Interestingly enough, your significance level for age will be the same as this F test up here, this probability for the F test, the p-value. Now, that's not as evident because all three of these look the same, but the intercept is a different p-value. It's just very small. We can use the circle trick and jump and see that this one is actually 88.43 e to the negative 14, and this one right here is 1.342 e to the negative 9. So these are really, really, really tiny numbers, but this one of this 1.342 is going to be the same as this one right here. If I can get it to do it, 1.342. Those two are the same. Same test is done there. So let's go ahead and do this problem now that we have kind of figured it out. We're going to take this regression equation right here and just copy paste the first few numbers. And the other number is 957. Rounds up. And make sure to put your negative right there. Explain the slope of the line. The car's value is going to decrease as we stated. Explain the Y-intercept. The Y-intercept is a car with 0 years of age, so it's a brand new car. If you want to sell a 6-year-old car, what price seems appropriate? Now to do this, we take 6 and we put it in here for age. What we can do in jump is we can go over here to the line and go to Save Predicteds. I'm right under the red arrow for linear fit, and I go to Save Predicteds, and now in my original data set, you will see I have predicteds. If I didn't have a car with 6 years of age, I could simply type in 6, and it would tell me the predicted price. Jump will solve the equation for you, and we can now take that number right there and put it into the problem. Now, once again, if you're studying for the test, it's probably a good idea to go ahead and work these problems by hand. Just put 6 into your calculator when you're using that equation. Once again, put 6 in for age and solve the equation and see if you get the same predicted price. If you get the same predicted price, you've done it properly. You have a chance to buy 2 cars. One has a positive residual and one has a negative residual. Now, what I like to pretend here is that these are the exact same cars, just 2 different people trying to sell it to you. Maybe it's a husband and wife or 2 different dealerships that somehow have access to the same car. So you're going to get the same car no matter what. With this in mind, let's look at our model. Something with a negative residual would be down here. Its actual is lower than its predicted. And we have a decent scenario up here with these two where this has a negative residual and this has a slightly, albeit very small, positive residual. It is above the line of prediction. So when we look at these points, we'd much rather buy the one with the negative residual because its actual price, denoted by this scale over here, is lower than the actual price of the one with the positive residual. Residual is how far off the line is. If we were to draw a line straight down to it, this red line and the distance from it is its residual. Anything below has a negative residual. Anything above has a positive residual. We often talk about the residual wrap. Residual wrap is actual minus predicted. The actual is the point and the predicted is the line. If the actual is above, the predicted would be smaller and we'd get a positive value. So in this instance, with 2 cars for sale, I'd much rather buy the negative car, the one with the negative residual. How can the residual of the price be interpreted? So the one with the negative residual costs less than the model predicts. We can see that right here. This one right here has a negative residual, and the model predicts that it's going to cost less. It costs less than the model predicts. Once again, this car right here costs less than the model predicts. You see a for sale sign on a 9-year-old car stating the asking price is $3,502. What is the residual? Well, they have the asking price. To get the residual, we need the predicted price. Going back to our data set right here, we can get the predicted price by plugging it in. As you notice, I do not have any sort of 9s here. But since I've saved the predicteds, it'll run the formula for me. So I can take this number here now and subtract the 2 numbers. We take actual, which is 3,502, minus predicted, negative 2,165.49. I always like to take the full number right here, copy it in, and this number would not round up, so I can just delete off everything right there. Once again, residual is actual minus predicted. We know the actual price. We had to find over here the predicted price using our data set to find the predicted price of a 9-year-old car. If you wanted to do that by hand, you can go right here and plug in 9 into your equation and you'll get the same number. Once again, that's a good way to check to see if you're ready for the test because you won't have jump on the test. Scrolling back down, would the regression model be useful in predicting a 23-year-old car? And the answer is no. This is an example of extrapolation. This is well beyond the scope of the model, and when we say extrapolation, we're talking about outside of the X space. Extrapolation. Over here, a 23-year-old car would be, and our model doesn't do that. And plus, we can see that it's going to go negative. If I start extending this out to where a 23-year-old car might be, it's going to predict a negative price. And I would love it if someone would give me money to buy their car, but that doesn't happen. So it's negative, and also it's an example of extrapolation. Going on to the next problem right here. We have an instructor tip telling us that we need to put the data into jump, and we should use the last point right here, the make tab to eliminate a copy. I'm opening up a new data table right now. I used Control-N to do that. You can always go to File and New and Data Table. Control-N will bring up new data tables or new Word documents or new Excel spreadsheets. We are going to paste with column names, edit paste with column names, and get our data in there. So with that in mind, we can do the analysis once again of a fit Y by X. We want to see fat predicting calories. So let's take a look at this right here. Fat predicting calories. Well, this problem is actually way easier than it seems, because if you notice, fat has a scale down here of about 18 to 29, and the only one with that scale is right here. This is the only plausible one. Make sure you pick the right one and just look at the scales. Interpret the R squared. We did this for our last problem. We didn't even have to, but it's always good to interpret it. Let's go ahead and get the R squared. 0.6960. This would mean that 69.6% of the variation in calories, our Y, is explained by fat, our X. X's do the explainings of the Y's. So right here we have 69.6% of the variability in the number of calories can be explained by the variability in fat in fast food burgers. Excellent. Write out the equation. And here's the thing. They want to make sure you know the proper format, that we are trying to predict a Y, and that the X is over here. So we have predicted Y equals 211 plus 15.678 times X, which is fat in this case. And this gives you the predictive equation, which you will then use later on. Use the residual plot to examine if the linear model is appropriate. Now we can get the residual plot by plotting residuals here, but we can also think about what it's going to look like. To get a residual plot, just make this line flat. If you notice, this point has a very small positive residual, then we have 3 negative residuals and 3 positive ones. So we should see small, 3 negative, and then 3 positive. Let's look at that. Scrolling down here, we see it right here, small, 3 negative, and 3 positive. Now, this does look like almost an example of does the plot thicken. There are issues here, but for this problem, we will choose that the linear model is appropriate. I don't like this problem that much. It's not a good example of a textbook problem, even though this is a textbook problem. But when we think about this, we want to see no pattern in the residuals. That's good. It's telling us that there's no sort of bend or unexplained variation or some sort of thickening where the model's getting really good predictions at the start and then it gets worse at the end. So let's go ahead and say this has no pattern, even though it's not perfect. And that should be the answer for 99% of your questions on this. Explain the meaning of the Y-intercept. Well, let's look at the Y-intercept on this model. For the Y-intercept, what would be 0? Fat. So this is a fat-free burger. And the value of the Y-intercept is 211. So a fat-free burger would have 211 calories. Explain the meaning of the slope of the line. The slope of the line would be for each additional gram of fat, we would expect an increase in calories by 15.678. And we see that basically right here. Remember, for each additional X, we would expect Y to increase by blank on average. Very important to always put these in context of the problem. A new burger contains 21 grams of fat is introduced. According to the model, its residual for calories is 3.936. How many calories does the burger have? Now to understand the residual, let's look at the plot. When something has a positive residual, its predicted is lower than its actual. So the point would be above. So if we take the predicted right here and add on the residual, we will get the amount. Remember, predicted plus residual will give us the actual. Our formula is residual equals actual minus predicted. So just bringing over the predicted to the other side, residual plus predicted equals actual. Let's get our predicted right here. We can do the same trick before using jump and go to Save Predicteds. Going back to our data set, we have a burger introduced with 21 grams of fat, and we have a predicted for this burger of 540.231. And I will say this, some people do not carry out enough decimals. I've seen people get this wrong by simply just not carrying out the decimals. So I'm carrying them all out in 3.936. And right here we get this. And let's put it in and delete down till we have 3 decimal places. And I will round up right here and we will see the right answer. Good luck. Make sure to carry out all your decimals and email me if you need any help.